Welcome everyone. Today we're very happy to have Gabriele and Ubaldo from Saclay, who's going to tell us about ADS3 RMT to Duality. All yours, Gabriele.
Thank you for the introduction. Before starting, I would like to thank you all for inviting me. It's very exciting to be here, and I look forward to having some simulating physics discussions during my visit. Now, today I'll tell you about, I'd like to tell you about wormholes in 3D gravity and the relationship with random matrix universality in 2D CFT. In particular, my goal is to convince you that wormholes can be seen as being emergent from the dynamics of chaotic conformal field theories. So let's start from the gravitational path integral. So the Gibbons-Hawking prescription for the gravitational path integral is the assumption that when we evaluate the path integral on Euclidean geometry with periodic time, Euclidean time, we interpret this as computing a trace over some Hilbert space of microstates. Okay. And this has been extremely successful, even though it is an assumption, it's proven. However, if you include also wormhole geometries, in general geometries with multiple boundaries, and here I will always be in ADS, okay, then there is not really an immediately clear way to understand them. So I think the first two questions that come to mind are, first of all, why should we include them in the path integral? And if we do so, what are they actually computing? And is there a similar Gibbons-Hawking prescription but for wormholes, where it's telling us what the wormholes are computing in terms of microstates? Okay. So I think the first question can be answered by the fact that they're very interesting, and especially in recent years, it's been found that wormholes actually are very important to capture various aspects of non-perturbative black hole physics. And just two examples that I will mention are first the role of replica wormholes in recent calculations of the Page curve for unitary black hole evaporation. And then the second example are Euclidean wormholes, which have been found to describe the long-time behavior of black holes. And today I will concentrate mostly on the second type of wormholes. However, I believe that the lessons we gain from this could be applicable to general wormholes. Right. And now, the second question, what are they actually computing? So if we want to justify the fact that we can solve all of these nice puzzles about black hole information by using wormholes, then we should first know what these wormholes are actually computing, not just assume that they're giving some contribution to the quantity that we're interested in. Okay. And a way to, a framework to try to address this question is, of course, ADS-CFT. Okay. But if we try to understand wormholes in ADS-CFT, we immediately run into a puzzle. She said, in ADS-CFT, contributions with two disconnected boundaries should factorize. While instead we can see that summing the trivial topology plus wormhole contributions does not factorize. And this is so-called factorization puzzle. Okay. Now, one way to understand this factorization puzzle is proposed by 2D JT gravity. In that case, 2D JT gravity is dual to an ensemble of random matrices. And thus, the wormhole is actually computing an average of a product of partition functions, where the average is taken with respect to the Hamiltonian. Okay. So the Hamiltonian is treated as a random matrix. And since averages need not factorize, then there is actually no factorization puzzle at all. Okay. However, this, to me, this only moves the goalposts of understanding wormholes. Because now we have questions regarding this, the role of ensemble averaging, especially with regards to higher dimensional ADS-CFT, which we know from many examples that works very well without any kind of ensemble averaging. Okay. So how should we interpret wormholes in examples of ADS-CFT without averaging in higher dimensions? And secondly, we expect that black holes have random matrix statistics. In particular, the energy levels, the black hole microstates will exhibit some form of random matrix statistics. And in higher dimensional ADS-CFT, this should be reflected in the dual CFT. So how can we find these random matrices in D larger or equal to 2 CFT? Now, the concept that will tie these questions together in the rest of my talk is that of random matrix universality. Okay. And to state simply, is random matrix universality is the fact that energy levels of chaotic quantum systems are distributed according to random matrix theory. Okay. So the Hamiltonian of a chaotic quantum system behaves as if it were a random matrix, with the following correlations between energy levels. Okay. One observable that we can use to probe this random matrix behavior is the spectral form factor, which is given by this analytic continuation of the partition product of partition functions. Okay. And here there's the typical phenomenology of the spectral form factor for a chaotic quantum system. And we'll be interested in this middle part, so-called ramp, which is exactly the part of the spectral form factor that diagnoses this chaos under the form of random matrix statistics. So the prediction is that random matrix statistics is encoded in a linear in time, approximately smooth linear in time behavior. Okay. Now, how do we compute this in gravity? In gravity, it's been shown that wormholes can reproduce this smooth linear ramp in the spectral form factor. Now, if we view this through this new lens of random matrix universality, could this mean that wormholes are an emergent feature of chaotic systems, just like random matrix statistics? Meaning that, an individual chaotic system is not a random matrix, it has fixed a specific Hamiltonian, but it looks like a random matrix. So could wormholes also be an emergent feature like that? And secondly, again, how does this RMT universality appear in higher dimensional CFTs? Right. So today I will focus on ADS3 CFT2. And in this case, it's well known that 2D CFTs have to satisfy very stringent consistency conditions coming from symmetry, Virasoro symmetry, and also from modular invariance, meaning that the partition function on the torus must be invariant under SL2Z transformations, which basically exchange the various cycles, the two cycles of the torus. Okay. How can we identify and quantify random matrix behavior consistently with such stringent constraints? And is it even possible to have random matrix behavior compatible, fully compatible with these constraints? So from the CFT side, we will be addressing this question. And now from the gravity side, in ADS3 pure gravity, Kotler and Jensen computed a two-boundary torus wormhole amplitude, okay, that denoted by ZCJ, Kotler-Jensen. And this computation, well, this geometry is off-shell, so it doesn't satisfy equations of motion of 3D pure gravity. And the way they computed the partition function was, let's say, subtle. I would say more later. So we would like to understand this computation better. And it was found that in the strict low temperature limit, as beta inverse temperature goes to infinity, this exhibits that smooth linear ramp characteristic of random matrix behavior. Okay. And people in the original paper too, it was proposed that this wormhole should be interpreted as the canonical version of something like the two-level density, with some brackets and denoting some form of averaging or ensemble, and they mentioned the words random CFT, whatever that actually means. And so we're left with many questions by this wormhole. Okay. So the first one is, what is this Z of tau 1 and tau 2? So what are the dual CFT partition functions that this wormhole is telling us about? And secondly, can we justify this very subtle computation in some other way? Okay. And then this low temperature limit, of course this is just one limit of the full amplitude. What is the rest of the amplitude telling us? Is it also related to random matrix theory or not? And finally, what are actually these brackets? Can we give an actual proper definition of those brackets, such that we can properly interpret this wormhole. Okay. So these are some of the questions that will guide us throughout the rest of the talk. And today I will present a framework for random matrix dynamics in ADS3, CFT2. And applying this to the Kotler-Jensen wormhole, we will obtain a microscopic CFT explanation of this wormhole. And we will learn many things, among which the following. So we'll see that random matrix behavior of CFT and wormholes can emerge dynamically from chaos in the spectrum of microstates. Secondly, we will learn that ADS3 pure gravity is what we call maximally RMT, meaning that it is as close to random matrix theory as it is possible by the symmetries. Okay. And this, we will identify this as a principle of maximal chaos. And finally, we will be able to factorize the Kotler-Jensen wormhole. Okay. And the factorized piece will be a new microscopic off-shell contribution to black hole entropy in 3D, which will denote ZRMT. Okay. So, to give you a preview of how we're going to actually do these things, so let me start with this image. So on the right we have the Kotler-Jensen wormhole, and on the left I've represented a product of CFT partition functions as some bulk geometry where, let's say, I don't know exactly what's going on in the bulk, but I have some factorized bulk geometry. And we'll show that first, we can take a product of CFT partition functions and perform a well-defined, mathematically rigorous form of coarse graining that will give us the Kotler-Jensen wormhole. And then we can also invert this and factorize the Kotler-Jensen wormhole. And thus we will obtain the exact expression for the CRMT partition function. And we can think of this as a new piece of the partition function of ADS3 pure gravity. Okay. So the partition function of pure gravity will be approximately given by this first term, which is also called Maloney-Witten partition function, which counts all on-shell solutions. Okay. So all of the on-shell solutions are included here. And now there's this extra term, which encodes the chaotic substructure of the black hole spectrum in 3D. Right. So, yeah.
This type of formula only applies when you put the CFT on a genus 1 surface, because when you put it on genus 2, you also have wormhole contributions that are on shell. Right?
Yeah. So this is for torus partition functions in CFT.
But yeah, the logic only applies.
I think similar logic should apply in higher genus cases, but we haven't developed that because you need to deal, like the mathematical machinery will be different, basically, because then you need, instead of SL2Z invariance, you need SP4Z, and you will have, you'll see, you can probably do something similar. But it is true that this case is special because there's no on-shell solution with two torus boundaries, while in higher genus you can find on-shell solution.
Can you comment how this work is related to work of Andreas and various people that seem to also look at exploring factorization?
Yeah, we will see that. So basically, I think it's kind of I would like to understand the connection more precisely, but it seems that it's really like you can really see this as a half wormhole. Okay, as proposed by people and others, and also you can similarly, you can think of this in various ways. Like for example, they have this nice paper on gravity factorized with Andreas, so on, where here they call this some correlated space-time grains, and we see that this partition function does have some properties that also their models have. Like for example, it will have some erratic behavior. It will be non-self-averaging. So I think it is at least a proposal for a 3D version of those.
The contribution for one form still existing, geometrically still exists in factorized form. The other thing just canceling, non-factorization.
Yeah, here it still exists. Yeah, in that case they only have like two geometries contributing, right?
One hole,
yeah,
plus some other contribution which cancels the non-factorization.
Yeah.
And if they average,
so here we will have, so we have these two contributions. So this is just the trivial saddle, the disconnected part, and this is the half wormhole part. Okay? And so this one under, if you perform some averaging, this one vanishes, but this one doesn't. So
it's not using.
It's yeah, structurally it's the same. Yeah.
Can you find the RMT such that the total thickness, like the discrete spectrum, like no continuum at all?
That's the future challenge, basically. But yeah, for now, with this VRT, it's not enough. Because basically this is like saying that, you know, just from the ramp, so this ZRMT encodes the ramp, basically. So as you know, this is not enough to look to find discreteness of the spectrum. So you will have to first include a full series of corrections to arrive at the plateau, and then let's say do a quantum corrected wormhole and then factorize that to get something like a discrete spectrum. Alright. So I will start by discussing so-called trace formula for 2D CFD. And to do that, we first have to isolate the chaotic part of the spectrum in a 2D CFD. Okay. So, and we would like to do that in a way that respects modular invariance. Okay. So, you know, this at first sight might be obvious, right? I mean, we know black holes are chaotic, so just let's look at the black hole part of the spectrum in 2D CFD. Okay, which is conformal dimensions above the C-1/24. However, this is not modular invariant, because SF2C famously relates the light part of the spectrum to the heavy part. Okay. And in particular, what it does is that given the contribution of one light state, modular invariance gives you continuous density of heavy states, basically some kind of background. Okay. And so we need to first subtract that background to isolate the chaotic part. And we can actually do that, that's accomplished by the following decomposition of a CFD partition function. Okay. So the partition function of primaries of a Virasoro CFD with C larger than 1, meaning that don't have any extra currents, can be written in terms of two pieces, okay, which are now defined. So the first one is just comprised of this background, the light states plus their modular images. And you can build it very easily. So you just first consider the partition function of light states. So you just consider sum over light states. And then you complete it by summing over all of their modular images. And this is just the minimal choice to arrive at a modular invariant function. And now the other part is this chaotic part of the spectrum. It's supported only on the heavy part of the spectrum, in the black hole part of the regime gravity, because we've subtracted off these heavy states. I think it's more clear to think about it from the microcanonical point of view. So the density of states of a CFD will be decomposed into these two terms, the light part and the chaotic part. Okay. And here we have that this black line, which oscillates, is the full CFD density, which here I've drawn for visual aid as a continuous line, thinking about, for example, the large central charge limit, where the mean difference between energy levels is exponentially small. But in principle, this is a discrete series, a discrete sum of delta functions. And we have that this kind of mean density in dotted lines is given by the light states. While the chaotic part are the oscillations on top of the mean. Okay. And they encode this quantum substructure, which goes beyond just the Cardi density of states. Okay, it's basically, you can think of it as Cardi plus some oscillations on top of it. And yeah.
Are these oscillations related to the oscillations that Clifford Johnson talks about, for instance?
So not necessarily, because so yeah, they are related to these oscillations from the fact that you have a discrete set of energy levels. Yeah. They're not oscillations related to, like, let's say, ensemble averaging or finite n oscillations. They're really related to the fact that, let's say, the full thing, so the full thing is a discrete sum over delta functions, okay, the full CFD density. But then you're decomposing into a first part, which is continuous, because the Cardi density is continuous. And so the resulting part, since it has to reproduce the discreteness, it has to oscillate on very, very small scales, which are proportional to e to the minus s. So, yeah.
Is this an actual graph, or is this just a picture?
No, this is just a picture.
Okay.
Really, in an actual CFT, these oscillations will be really extremely, extremely fine grained of order of e to the minus s. And yeah, it's just for imagining it. Now, this decomposition into this sum of mean density plus oscillations around it hints at a relationship with the so-called theory of trace formulas for chaotic quantum systems. So this describes the density of states of chaotic quantum systems as exactly a mean density, rho bar, and an oscillatory quantity. And by basically refining the semi-classical expansion of the Feynman, usual Feynman path integral, you can derive this following expression, which is called the Gutzwiller trace formula, for the oscillatory part. And this is expressed as a sum over periodic orbits of your chaotic system. So there's various ingredients. So you have these orbits, gamma, and then you have an orbit action, S gamma, the period, okay, and a one-loop determinant. So what this is saying is that the oscillatory part can be expressed as a coherent sum over classical periodic orbits of your quantum system. Okay. And of course, the suggested analogy is the following, that the mean density corresponds to the density of light states, and that the oscillatory part corresponds to this chaotic density. Okay. And now we'll see that we can realize this analogy precisely. So, we will use now a brief mathematical property, okay, which is that this chaotic partition function is actually a square integrable function. So that means that we can actually decompose it into a complete basis of eigenfunctions. In this case, these are eigenfunctions of the Laplacian on the fundamental domain of the torus. And the decomposition takes this form. Okay. So there are two basis elements, this ES and those phi n. But the real microscopic CFT data in this decomposition is encoded into the overlaps with respect to the basis elements. Okay. Now, I won't really need the mathematical properties of these functions for the rest of my talk. They're quite interesting, but I won't, since I won't need them, I won't say much. But they basically have some known Fourier expansion and some known properties that that you can use. But for now, let's not dwell too much on this. So let's see. This SL2Z decomposition of the chaotic partition function actually realizes this analogy with the Gutzwiller trace formula. And it does so in a way that a single SL2Z basis element, those ES and phi n, okay, correspond each to an individual periodic orbit. And we can see this because we can write a single basis element, okay, which now I've written like this, for some frequency omega, which just tells you which is the basis element, in the same way that you write a single periodic orbit. Okay. And we obtain these following identifications. Okay. The precise form is not important. The important thing is that you can identify some analog of the periodic orbit action, the period, and the one-loop determinant, just by demanding some simple conditions, which is that the action must be real and that you have a smooth scalar limit. So now we have this analogy between this decomposition of a CFT partition function and this trace formula for chaotic quantum systems. It's time to do something with it. And yeah.
Is there some system that you have in mind that actually has this action, this period, and this?
Yeah, that's a good question. No, unfortunately, no. But it would be nice to try to like find some toy model that has exactly these properties. Yeah, I don't know. This cosh minus 1 is kind of logarithmic, so it's basically like a log. Okay, and T, defined in a previous slide, is the twist. It's kind of like the energy above threshold in a CFT. So this is kind of log E behavior. It's funny because there's one case in which the trace formula does have like a log of energy form, which is for the Riemann zeta function. So if you think of the zeros of the Riemann zeta function as some energy levels, then they have a trace formula description, and it goes like log E, which is kind of suggestive, but yeah, I don't have any more.
So in the, I guess in the, if we take like the JT limit of this CFT, the Eisensteins become like the trumpets roughly, no? So is there then a strong analogy with what Phil and folks said about periodic orbits? Like
kind of, but yeah, I would like to talk about that more because I'm not. I wanted also to take in the future like study like properly a 2D limit of this, and we will see something like that, but in temperature. So I will go to low temperatures, and we'll see that it's kind of a reduction to 2D. But yeah, I'm not entirely sure at the level of the single Eisensteins what is a 2D limit of the Eisenstein. Yeah, but that's interesting. So now we've built this machinery, okay, and this will allow us to establish random matrix universality in 2D CFT. Okay. In particular, we can follow the same path that people do in chaotic quantum mechanics, okay, which is that you write down the microcanonical spectral form factor, okay, given by a product of the oscillatory part of the densities, and you perform some microcanonical coarse graining over some window that type. And I won't present the derivation, but there's a very famous result by Berry, which is that the leading substituting in the raw oscillatory, substituting the sum over periodic orbits, you see that the leading term in the spectrum form factor is given by the diagonal piece, meaning identical orbits. Okay. And this term reproduces the linear ramp in the spectrum form factor. So why is this important? Okay. Especially for us in high energy field. So Berry's diagonal approximation, what it does is it extracts the random matrix behavior, the chaotic system, from the oscillations in the density of states. So you can see this as some process of quantum interference in a single system. Okay. And secondly, there's an emergent non-factorization via this quantum interference, because the leading term is given by the diagonal part of the sum, and you're basically throwing out the off-diagonal part. Okay. This is especially interesting if we have wormholes in the back of our mind. Okay.
But this is because we average over some small energy window.
Yeah, states.
Yeah, so if you don't average at all, you will still see, for example, the averaging is more to smooth out the ramp,
Yeah.
basically.
Yeah.
But it doesn't mean that you are throwing out these terms by the averaging. So you can still do microcanonical coarse graining, okay, and then reproduce all of the other infinite series of corrections to the ramp. So basically, so up to up to like doubly non-perturbatively small corrections. Yeah. Yeah. Exactly. But yeah, it's not that the microcanonical coarse graining is not what's taking out this off-diagonal part. Else it would be like by hand, basically. Right. So we can do the same for a 2D CFT, which is that we've seen that orbits correspond to SL2Z eigenfunctions, so we should pair those. Okay. And we arrive at this 2-copy CFT partition function. Okay, where we see that indeed the basis elements are paired. So these are Eisenstein series and these are the cusp forms. So yeah, maybe I didn't say that. E are called Eisenstein series and phi are called cusp forms. But yeah, we won't need any of the details. Okay. And they're paired diagonally. And now, why did I call this Z-Hecke instead of Z-diagonal? Okay. And the reason is that you can actually define rigorously, a mathematical way, this diagonality using something called Hecke operators of SL2Z. I'll also spare you the mathematical details, but you can really write Z-Hecke as a projection of a factorized product of CFT partition functions. Okay. And the projection projects onto the kernel of an operator. okay, which is defined in terms of these HEP operators. Now, a more physical way to think about it is that you can think that a function CEA that satisfies this property, so that this lies in the kernel of this operator, has an enhanced symmetry. Okay. Why? Because it's annihilated by an infinite set of commuting operators. So you should think of this projection as some like enhanced symmetry. Now we're ready to go back to the spectral form factor into the CFT and identify a condition for a CFT to have a rank. So in general, spectral form factor is given by this expression where I have some kind of brackets to smooth out the linear ramp. Okay. And the factor in front is just due to taking care of Virasoro descendants. Okay. Now, a key fact is that in our decomposition of the partition function, where we have the light part and the chaotic part, you can show that the light part only contributes to the decaying part, the slope of the spectral form. Okay, so to focus on the ramp, at late enough times, we have that the spectral form factor is given by this diagonal partition function that we learned in analogy with berries. Okay. So we're interested in this kinematic regime, which is Lorentzian or SFF kinematics, okay, where we analytically continue the temperature, which is this y, which is the imaginary part of tau. Okay. And we now define these new variables, r and z. So r is just square root, the product of temperatures, and z is the ratio of temperatures. Okay. And the late time limit with temperature over beta, time over beta fixed, corresponds in these variables to large r with z fixed. Okay. So to understand this, this is the z plane ratio of temperatures, and we will be in this half circle for the spectral form factor kinematics. And in particular, very late time limit corresponds to z equals -1. So now we want to study this CEA in this regime, this kinematic late time regime. Okay. And for simplicity, and also it would be useful later when we discuss wormholes, I discuss just the spin zero sector of CEA. And we see that in this limit, so there's a universal linear in R behavior, and the full behavior of this partition function of the spectral form factor is determined by this R of z quantity. Okay, this will be an important quantity. And this is determined by the CFT data. Okay. It's an inverse Millen transform of the CFT data. And this R of z really fixes the low temperature behavior. So we're now ready to establish random matrix universality, and we can find a sufficient and necessary condition for a 2D CFT to have a linear ramp. And that is that with CFT will have a linear ramp if and only if this R of z has a simple pole at z equal -1. Okay. Now you see here that we can translate this into a condition on the CFT data, which are the overlaps. And doing so, it's interesting. It has some notable properties with respect to the previous characterization. First, this becomes an asymptotic fall-off condition on the overlaps, okay, as the frequency omega goes to infinity. But the really interesting thing is that this condition on the linear ramp is now microscopic, okay, since the overlaps are really the microscopic CFT data, while instead the linear ramp is usually a coarse-grained property. Second is practical. Okay? If you give me a CFT partition function, I don't need to do coarse graining, I don't need to plot the spectral form factor, I can just check this condition for the overlaps. And finally, this condition, together with SL2Z, implies a set of universal corrections to the linear ramp. So to the CFT, you cannot have only a linear ramp. Modular invariance will give you an infinite set of corrections to that. All right, now we're ready for the fun part, which is a convergence wormhole. So first, recall a familiar concept in gravity, which is that since gravity has to be invariant under large diffeomorphisms, okay, this invariance is often realized, especially in ADS3, as a sum over geometries. Okay. And in particular, this sum over geometry is implemented as a sum over boundary moduli. Okay. So if you have a torus, this sum over geometries is implemented as a sum over SL2Z transformations of the boundary torus. Okay. And so for wormhole amplitude, torus times interval topology, it's reasonable to make the following ansatz for the generic form, which is an SL2Z sum now over relative twists of the boundary torus, with some seed function f0, which will be generic, can be anything. And now what we want to do is interpret this wormhole, this general class of wormhole amplitudes as instances of a CFT quantity, which is this HEP-QIS that we defined. Okay. And that's finding a wormhole fairy tale, if any of you ever recall the old black hole fairy tales. So first, to establish this correspondence, we can see that wormhole amplitudes, just by virtue of having this general form, have special mathematical properties. Okay. So you can prove that any function which has this sum over SL2Z has Hecke symmetry, okay, which was this enhanced symmetry that the Z Hecke has. So wormholes indeed give diagonal, just like in Berry's diagonal approximation, give diagonal correlations in SL2Z space. Okay. And moreover, if you write the wormhole amplitude in this SL2Z basis, the decomposition is kind of maximally simple. Why do I say that? Because, okay, it is diagonal, but it's also determined by a single function, which I call this f wormhole of S, both here and here, while in principle those two could be independent. And you can show just from this form that the full wormhole amplitude for arbitrary tau1 and tau2 is completely fixed by this quantity that I mentioned before, R of Z. So R of Z, we found it in the scalar sector at low temperatures. Okay. And so this scalar sector low temperature R of Z is enough to fix the full amplitude for all temperatures and all spins, thanks to this form of the wormhole amplitude. Yeah.
Can you remind us what was the form of this Hecke operators? Are they
I went a bit quickly through that because sometimes it's So this Hecke, you basically define this operator. So T, J of tau1 are Hecke operators, okay, and they act on the basis functions as follows. Okay, since this is a complete basis, this completely specifies direction.
And I should think about them as some differential operators on top?
They're not differential, they're really like they implement some sum over some coset of SL2Z, okay? But basically they map modular forms into modular forms. They're an automorphism in the space of modular forms, okay? But basically the way you should think about them, okay, is that here we're considering a difference of Hecke operators between tau1 and tau2, okay? And we see that wormholes have this Hecke symmetry, okay? Meaning that this f of tau1, tau2 is a wormhole amplitude, then this difference of Hecke operators annihilates it, okay? So from a bulk perspective, you can think them as some operator which is sensitive to whether the bulk is connected or disconnected, okay? Because if you instead take a factorized function of tau1 and tau2, it will never be 0, okay? So it is somehow in the bulk. I mean, we don't have like a bulk realization of these Hecke operators, but it seems to be something that that can see if there's a smooth connection between.
So you don't yet know the geometric meaning.
No.
How they act on the metric.
Yeah. We know that wormholes have this Hecke symmetry, okay, but we don't know. It seems like it's some kind of topological bulk operator, okay, which tells you if your geometry is smoothly connected, okay, but we don't have a bulk realization. Yeah, I was here. So we found that these wormholes have this Hecke symmetry, and that they're entirely fixed by this quantity R of Z that we use to characterize the linear ramp in CFT. So now we're ready to answer question 2 from the start of my talk. So what are the wormholes computing? Okay, they're computing ZHEP, okay, which is a coarse-grained diagonal 2-copy CFT partition function, and the correspondence is as follows. So this F wormhole is the wormhole data, which appears in this form, this decomposition, and it's related to the CFT data, which are these overlaps on this basis of the CFT partition function. And the same holds for the files, for the task force. Okay. So we've realized this wormhole fairy tale, meaning that we now have an interpretation of what a wormhole amplitude is computing from the CFT point of view. Now let's apply this to the Cotler-Jensen wormhole of ADS3 pure gravity. And it will turn out that this formalism is really the key to unlocking the secrets that this wormhole wanted to tell us. So it is clearly of this form, the Cotler-Jensen wormhole with this sum over relative modular transformations, and the sig function is just this very simple function. Okay. And as I mentioned at the start of my talk, so this is an off-shell computation, okay, and it was computed via a so-called method of constraint instantons, okay, and we wanted to try to justify this result by other means. And secondly, it's known that this exhibits random matrix behavior strictly in the low temperature limit. Okay? But what are the corrections? What is the full amplitude telling us, not just the low temperature limit? Okay? And I will answer those questions, and we'll do so by first, we will find where the Cotler-Jensen wormhole sits in the full allowed space of wormhole amplitudes. Okay. And secondly, we will interpret Cotler-Jensen microscopically as an instance of this diagonal partition function in CFT.
All right. So is it immediately like checking around this F0? Like random time.
Yeah. If you apply the HEP operator, it will change around. Yeah. You will basically get like another sum over some coset, over some matrix group. But it turns out that you can swap around the sums and the whole thing is invariant.
So if you do like the bulk thing, is a kind of superposition of orange there? The bulk realization is just a changing superposition.
Yeah, it's kind of like a superposition of various topologies in bulk. Yeah.
It's equivalent of course at the boundary, but it's you can decompose it and it's changing around.
Yeah, so it's kind of like in the end the answer is invariant. But because of large invariance under large diffeomorphism, but at the level of single saddle points, it maps saddle points into each other.
Yeah, because you're talking about the bulk.
Yeah, exactly. Yeah, that's a good way of thinking about it. So now we can write the Cotler-Jensen wormhole in these spaces, and we find that it's given by, it's specified by a very simple product of gamma functions. These bases, which is nice. And
so the two Eisensteins are a double sum over modular images.
The Eisensteins, you can write them as a sum of.
So you have a double sum here, and on the TV space page you have a single sum.
Yeah.
So is there intuition for what happens with one of the seemingly infinite sums? It gets regularized in some. So is it state regularization?
Yeah, it's a good question. No, I'm not sure. I haven't looked at that. So what he's referring to is that you can define this Eisenstein series as an SL2Z sum of y. Okay, y to some power. It's a very simple one. And so he's saying, okay, here, if you write that, you have a product of SL2Z sums, but on the left-hand side, you have only one SL2Z sum. How does that happen? Yeah, I don't know. I should try to do a calculation.
I always found it a bit confusing in the Cotler-Jensen world that it's one sum.
It actually, maybe at first, but then if you think about it, so geometrically, the fact that it's one sum comes from the fact that in general, for if you have some arbitrary bulk topology, And this for hyperbolic manifolds, which is not the case for Kotler-Jensen, was proposed in this paper by Scott Collier and Lawrence Eberhard and Chang, that the sum over geometries takes the form of a sum over the relative over the boundary mapping class group, okay, of delta m, one manifold, quotient by the relative mapping class group between the bulk and the boundary. Okay. So if you apply this rule, which holds for hyperbolic manifolds, to this case, where it's not proven to hold, but you get this relative SL2Z. Because here you have two SL2Zs, right, because of the boundary terms. But here you also have one SL2Z, because of the relative twist. And so by doing a quotient, you get a single SL2Z. Basically, one SL2Z is cancelled by bulk diffeomorphisms that act in bulk, but not in bulk.
So some of these math customers have this arithmetic chaos, and they're not analytically.
Yeah,
how do you know these overlaps analytically?
Yeah, that's a great question. So it's thanks also to the fact that the Kotler-Jensen takes this form of Laplace sum over SL2Z. So it's basically one of the very few classes of functions where you can compute these overlaps analytically. So if for a generic modular form, computing its overlap with a CAS form is not possible. But for Poincare sums, you can do it. Poincare sums are these SL2Z sums. Yeah, I can show you. So we have this Kotler-Jensen wormhole, and now we remember, as I've emphasized, that a wormhole amplitude is entirely fixed by this R of Z function. Okay. And so we can just look at this R of Z. Okay. And we find this amazing fact, which is that the Kotler-Jensen wormhole is exactly given by the linear ramp. So we had seen that the linear ramp corresponded to a simple pole at Z equals to -1. And it's exactly this. Okay. So it's not just given asymptotically. Okay. In principle, for a generic chaotic CFT, you will have this pole at Z equals -1, but the rest of the analytic form of R of Z is completely free. While here you have no other corrections. So this shows that the CJ wormhole is extremal in the space of wormhole amplitude. Okay. It's exactly given by the random matrix theory prediction without any corrections apart from those implied by symmetry, like modular invariance. Okay. So now let's take a little time to understand what this result is telling us. Okay. So this result reveals that ADS3 pure gravity exhibits random matrix statistics to the maximal possible extent. And we denoted this principle as max RMT. Okay. So meaning the maximal realization of random matrix universality compatible with the symmetries of your system, which in the specific case of ADS3 CFT2 are Virasoro symmetry and modular invariance. Okay. In other words, okay, we can rephrase this to understand this better. So Kotler-Jensen is the minimal completion of random matrix theory compatible with Virasoro and SL2Z.
Why can you say that open density is a pure ADS3? Because you may have the fluctuation from constraint to
from the
because there is always a constraint in something. It's just only thinking about values, right?
Yeah. So we
but ADS3 gravity may have deviation from the results.
From this from the Kotler-Jensen result?
No,
I think that at least the point of view we're taking is that the Kotler-Jensen wormhole is giving the answer for pure gravity. Okay.
No correction.
You mean like higher genus? Yeah. That, yeah. Okay. Yeah. Of course. You can have, let's say, I will talk about corrections in a second, but we expect those at least to be non-perturbatively suppressed. Like, let's say, higher genus wormholes, and so on.
So your statement of maximum chaos is up to.
Yeah, it's about the linear ramp part. So even in random matrix theory, the linear ramp is just a series, in the first term, in a series of infinite corrections. So if you want to probe this statement to all orders, okay, then you should match each term in this infinite series of corrections. What we're doing is matching the Kotler-Jensen wormhole to the linear ramp term, okay, which is the first one of our term. But ideally, I think a good picture is that higher genus wormholes will give you the full series predicted by RMT. But this is conjectural. We'll probe that first. So, a second way to say this is that Kotler-Jensen is exactly dual to a matrix integral after you correctly process the symmetries of your system. All right. And finally, we can interpret this statement as a principle of maximal chaos. So this max RMT extends the notion introduced by Maldacena, Schenker, and Stanford that gravity is maximally chaotic. And for them, they were considering Lyapunov chaos, so diagnosed by the Lyapunov exponent, at early times, semi-classical. While max RMT extends this to random matrix type chaos, which is valid at late times, and it's really fully quantum chaos. And more specifically, so the condition for maximal chaos for them was the saturation of the Lyapunov exponent, while for us it's a bit, it's not as nice as just an inequality, but the point is that you're saturating RMT universality over parameter space of your theory, which can be spin, can be temperatures, chemical potentials, and so on.
So more concretely, it's just characterized by how far the function R of z is from just being 1 over z minus 1?
Yeah, exactly.
Okay.
Yeah. Or you, yeah. All right, so now we write the final part where I will factorize the Kotler-Jensen wormhole and see what we can learn about black hole microstates in ABS3. So recall a key fact from the start of my talk, which is that this CFT trace formula, this SL2C decomposition, expands over a complete basis. Okay. So the fact that the basis is complete means that we can actually uniquely factorize the Kotler-Jensen wormhole. How? Well, we write this form, which is on the left-hand side, we have the Kotler-Jensen wormhole, and we set this equal to a Hecke projection of CFT partition functions, okay, which we call ZRT. Okay? And this is an actual equation that you can solve. Okay? And so we can take Kotler-Jensen, factorize it, and to find what are these microscopic CFT overlaps of this ZRT. Which are given under this suggestive form by the Riemann zeta function. It's a well-known object related to chaos. So this means, this statement means that the CFT, a putative CFT dual to ADS3 pure gravity, has approximately the chaotic partition function equal to the CRT. And we see how, as I mentioned at the start of the talk, that by taking a factorized product of CFT partition functions, we see that the wormhole emerges dynamically via this mechanism of diagonal, various diagonal approximation. So now I think it's time to make a few comments on this whole story about gravity being one-to-one ensemble average. Where does that leave us? So in ADS3, individual saddle points, okay, Kotler-Jensen was not a saddle, do appear to be dual to some kind of average of CFT data, or at least some universal properties of CFT data, that was shown recently. However, although semi-classical gravity seems to compute some averages in a statistical sense, to my knowledge, there's not a bulk computation that can distinguish, that can tell you what kind of averaging you're doing. So the more robust concept, I believe, is apparent averaging, as was presented at least in our community by Schwenker and Witten. So apparent averaging emerges from chaos in the black hole spectrum and the larger limit of the Hilbert space of black hole. And our results are a dynamical realization of this principle of apparent averaging presented by Schwenker and Witten.
Sorry, does this apparent averaging lead to factorization or not? I mean, does it describe?
Yeah, it's the principle of apparent averaging is consistent with factorization because you're basically saying that you see an averaging in gravity, not because you're actually doing some average, but because the black hole part of the spectrum has chaotic dynamics, and moreover, you're at large n, and the size of the Hilbert space of a black hole, as you change n from n to n plus 1, changes exponentially. So, okay. So this means that the black hole Hilbert space doesn't have a well-defined larger limit. Okay. And so that's why you see this apparent averaging. At least that was the reason. But from a more...
I'm just trying to understand what's being averaged over. So it's not theories, it's not Hamiltonian.
No, it's just simply, so you have, let's say, the energy levels, okay? But you're not probing them with the necessary precision to see the individual microstates, okay? And moreover, these energy levels have these random matrix statistics. Even though they're single energy levels of an individual system, their statistics, really just by counting them and putting them in.
Isn't that just mathematically?
Yeah.
Having some
I don't think so. So it's true that sometimes it feels like, okay, you're just changing words around. But one difference is that really whether you can factorize it or not. Right? So here, the point is that you do have a factorized answer, which you cannot have if you're just taking averages. Like in random matrix theory, you cannot factorize a correlation function. Okay. While in this case, if you have like some individual quantum system,
Wormhole is not a product of two things.
Sorry?
The Kotler-Jensen wormhole is not a product of two things.
No, it's not. But you can see that it is consistent with taking a product of two things and not doing some averaging, but doing some projection of this, some coarse grain. Which is the same way it works in chaotic quantum systems. You also see this apparent averaging, where you take really a single chaotic quantum system, and you see that it also behaves like an average, even though you have really a single system.
The apparent. So sorry, go ahead.
Yeah.
So that could be a way to define mathematically the averaging. Physically, you can't discriminate like those things.
Yeah. Yeah. So especially in gravity, I mean, in gravity, to distinguish individual microstates is not possible. But even more so, it's just like it seems like the gravitational path integral encodes information about the black hole spectrum in a weird way, which are through these wormholes. Okay. Yeah. I don't know if.
Yeah, this is
sure.
a way to present mathematically, of course.
Yeah.
You can take n goes infinity,
Yeah.
that exponential.
So you can really see that, I mean, this is, my point is that this is really a dynamical mechanism. Like we're not taking and doing some actual averaging over the CFD data. You can really see it in an individual quantum system that if you compute these observables, then the leading term will be given by this diagonal piece.
But this is still the same resolution where we say, okay, there's the wormhole which makes it look like it doesn't factorize, and then there's many other terms that come in that fix the problem. I mean, this was sort of described in Saclay and Stanford, for example.
So they do have indeed, in many of their papers, basically I think in almost every one of your papers you have some section on comments on non-theories without disorder averaging, and they exactly propose this mechanism of trace formulas. And this is a realization of that, which I think in JT Gravity there's not yet a full realization of this trace formula story, but there was this very nice paper where they took the first steps on doing this convergent genus expansion for the plateau. But it's exactly the mechanism I propose. So, first somebody asked about armed wormholes. So indeed, this ZRT, you can interpret it as an ADS3 half wormhole. So why? Because it shares these properties with the proposals for half wormholes in 2D gravity. First, it's a single boundary quantity. It's not self-averaging, okay, because of these oscillations. And we've seen how gluing two of them together, specifically in SL2C spectral space, produces a smooth wormhole. And finally, it has some erratic behavior, which was seen as a characteristic feature of half wormholes, for example, in SYK, because if we write the overlaps of ZRT, we write it in terms of modulus and phase, we see that there's the phase is given by this so-called Riemann zeta phase, okay, which I plotted here has these erratic oscillations. And this Riemann zeta phase actually appears in, it's a well-known object in the theory of chaotic quantum systems. So there are systems which have an S matrix given by this Riemann zeta phase, which these properties closely mirror the ADS2 picture of half wormholes, exactly like the papers we mentioned before. And here I've represented the convergence and wormhole in this annulus, broken annulus topology to mirror those two results, those 2D results. Finally, so going back to the path integral of 3D gravity, we've identified a new off-shell contribution to the 3D gravity path integral, this ZRT. And ZMWK, as I mentioned, sums over all the smooth saddles, which in 3D are classified, so we know those are all the saddles there are. And so ZRT must be off-shell, and it encodes the leading RMT fluctuations of the black hole spectrum. Okay. We can think of this as a corollary as saying that in pure gravity, the correlations between BTC microstates are as random as possible. However, this is not the whole story, as you mentioned. There must be corrections, and there are a variety of reasons why there must be. So first of all is RMT predicts an infinite series of corrections. So if we believe that we should find RMT statistics for black holes, then we should also think about this series of corrections. Then we also expect to have higher genus contributions in 3D gravity. But finally, I think this is the most rigorous argument why there should be corrections, is that these corrections are needed for unitarity. So the Maloney-Witten partition function is famously not unitary. The density of states is negative in certain regions of the spectrum, near extremality. And unfortunately, ZRT does many things, but does not solve the unitarity problem. Okay. So we need some corrections to solve those. And finally, I think this story should have many nice applications in the future, especially this diagonal mechanism. But I will leave you with two specific ones I have in mind, which go through the process of including this infinite series of corrections predicted by RMT. So the first application is, well, it was recently shown us that by people in this room that there's this so-called tau scaling limit, which shows that resumming corrections starts the transition to the plateau in the spectral form factor. Okay, and the plateau is closely linked to discreteness of the spectrum. Okay, so ideally, if you include this whole series of corrections in ADS3 and you reproduce the plateau, this will indicate discreteness of BTC black hole entropy. Okay. And secondly, unitarity of the gravity partition function. So also after including all of these RMT corrections, you can again factorize the resulting wormhole and see and extract these corrections. And I think there's a lot of evidence that these corrections should restore unitarity to the ADS3 gravity path integral, in particular from the work of Maxfield and Tuiachi, and this should complete their proposal. So thank you.
Questions for Gabriele?
I didn't quite understand in this slide in the end. Yeah. How do you propose to find these corrections?
So,
as in, so for instance, for Kotler-Jensen, you could invert this Hanke projection to get what Z spec of tau is. But how do you find corrections to that?
So, you're referring to the second part, right? To the
yes,
okay.
yes. Well, I guess for both you need to understand the correction.
Yeah, so ideally you implement the corrections. So RMT predicts these corrections at the level of the spectral form factor. So you will have to write down first a wormhole amplitude. Okay. The first term will be the Kotler-Jensen part, and then you will have corrections to Kotler-Jensen, which are exactly given by the RMT result. Okay, so you basically make an ansatz, okay, guided by RMT, and this tau scaling limit for a wormhole amplitude. And this R of Z, which in Kotler-Jensen is given just by the ramp, you can imagine that there you add a full series, infinite series of corrections.
Coming from the RT answer.
Coming from the RT answer. So you're kind of bootstrapping the answer. It's not a gravity calculation, at least what we're coming on. So you impose this series of RT corrections, okay? And you create basically a fully quantum corrected wormhole, okay, with all of these series of corrections. Okay. And this wormhole will have this tau scale behavior, okay, because you imposed it basically. Okay. But it will have it in ADS3, okay, because you will then dress it with the modular invariance and the Rosoro symmetry.
You're just saying that that's a way to obtain some tau scaling limit in a minimal way that's consistent with your Rosoro symmetry. Yeah. And, exactly. Much better.
Yeah. Indeed, this is still, I mean, it's not something we've already done, we're not to just write it down. There are some subtleties, like, because, for example, you need to choose some density of states, rho 0, for your matrix integral, right? The tau scaling limit depends on the density of states, rho 0. So you will need to get in JT the Schwarzian, but here, what would you use? Right? And there's, we've been thinking about what to use. For example, once you could use this chiral-Carty density that recently was used for this Virasoro minimal string. Yeah. But apart from these subtleties, the idea is you impose this prediction by RT, okay, and you get a 3D wormhole amplitude, which does have this tau scale behavior and does have this convergent expansion to the plateau. Okay. And then that's the first part. And then the second part is you factorize it. You extract this delta ZRT, okay, and you see if this cures the unitarity problem.
But for instance, in Maxfield-Toriachi, the resolution came from these Seifert manifolds.
So ideally, those
you
would
obtain those from random matrix theory. So get separating gradients, right?
I think that those will be included. So that the contribution that they gave from Seifert manifolds, so they computed it in 2D, and they have some. Of course, there's Seifert manifolds are 3D manifolds, but they didn't compute the full modular invariant contribution of those manifolds. So we think that actually those two things will be equivalent. So the contribution you will get from factorizing wormholes will include the contribution of those Seifert manifolds. Okay. And you don't see that from Maxfield-Toriachi because they're not, like, their answer is only in they only compute things in the regime where they need them, which is the near extremal large spin regime. And they do the 2D computation, okay? But if you do a full 3D calculation, which is fully modular invariant, and it's defined everywhere in the spectrum, not just at large spin near extremality, I think that should be included at least in the things you get from factorizing work. And I can tell you a bit more details of how the CRT should also be related to those Seifert manifolds.
Yeah. So one thing, so the Hacker projection, if I multiply the two partition functions, is it basically equating the S label of both of them? Like it's inserting like delta as 1 equals S2 or something?
Kind of, yeah. Not exactly that, because that's not enough like so you have to do that for both the Eisenstein and the Castorm part.
Okay, so the delta function is 1 to delta.
Yeah.
And you expect the higher genus corrections to also be diagonal?
Yeah, that's something we've been thinking about. I don't know. I think they should, but I don't have like a way of proving it. So suppose you have some higher genus work to convergence and work, right? Yeah. And here you have some higher genus. Okay. So I suppose this formula for computing the sum over geometries is correct. Okay. So you will still have some product of SN2Zs for the boundary here. Okay. But then you will have a more complicated bulk topology. And so I don't know if for higher genus wormholes, you will still get that your wormhole amplitude can be written as a sum over SL2Z transformations. Okay.
Sorry, can you say again what was the it was the mapping class group of what?
So this is a proposal. So this is I propose to hold for hyperbolic manifolds with this, and the idea is that once you compute your gravitational action on a fixed geometry, you implement the sum over geometries by summing over the elements of this group, okay? Which is the quotient between the mapping class group of the boundary of the manifold, okay? Which here is just 2 copies of SL2Z, okay? Quotiented by the relative mapping class group, meaning that if you keep, let's say, the boundary fixed, what are the relative modular transformations that you can do? Okay. So in Kotler-Jensen, that's 1 copy of SL2Z, because that's the relative transformations that you can do with respect to the boundary. Okay, so let's say you fix the boundary and you only twist the bulk. And that gives you a single SL2Z for Kotler-Jensen. Now, for higher genus, the numerator stays the same, so it's just 2 copies of SL2Z. But I'm not sure about what this object is for higher genus.
I'm just asking because I have a hard time understanding why it's a subgroup of the group at the. It's a subgroup. It's a subgroup of SL2Z in general.
It's a sub.
Is it a subgroup of SL2Z?
Of 2 copies of SL2Z. Yeah, of SL2Z times SL2Z.
But also presumably the relative. The relative transformation is smaller than SL2Z. At most, it's SL2Z.
Yeah, it should be at most SL2Z.
Okay.
That should be the case. But yeah, I don't know how to prove this. Mathematically, that if I have a genus 1 wormhole, this will. The whole point is, does a higher genus wormholes also take this form as a sum over SL2Z? Okay. So I don't know if that's true. If that were true, then it would immediately bias this diagonality in the SL2Z space. So and that would be very, very useful, because then you can really just use the same techniques. Else, if it's not true, then higher genus wormholes will also involve off-diagonal contributions.
Questions from Gabriele? If not, let's thank him again.